All right, welcome back. Monty here, week 12. Some of you just flew right through that rigid motion. It only took like 16 minutes in video. So let's try geometric components of rigid motions. Developing definitions of rigid motions. Let's see what that means. And this is going to be part of that notation where they're going to talk about how do we make sure that we write it properly. Okay, so rigid motion is a translation or a slide. That's one type. Okay, capital T for translate. Consider PQ. PQ is perpendicular to CB. Translate PQ using the translation function, translate from TR to PQ. Translate from here along here to here. To translate, first determine the direction of the translation PQ. Translate in the direction of TR of a distance MTR. Draw lines parallel to the translation TR to the point PQ. Draw the point P such that PP prime, TT prime. Therefore, we can say to translate PQ from here over to here. Wow. All right. Study the example and then answer the questions. Decide whether the statement about the example is true or false. P prime, Q prime is congruent to PQ. Yes, because they're between the two lines. True. P prime, Q prime is perpendicular to BC. Well, we slid it over. We didn't rotate, so I'm going to say yes, even though it's not on that line. Okay. Now the measurement of QQ is not the same It has to be the same. That goes to there, that goes to there. I'm going to say false. They're equal. PP prime, TTR, they have to be the same. Okay, because that's how we drew them. Okay, TR is parallel to QQ. Parallel, absolutely they're parallel. Okay, because we slid them. True. Complete the statement about the example. Line PQ was translate. All we did was slide in the direction of TR, because we followed TR, a distance of TR. Okay. Using the diagram below, show that we translate GK over to SV. Line GW is parallel to the line SV. The input of the function of the figure is GK. That's what we're starting with. Okay, so they're saying the input is right here, SV. Okay, the output of the function is S prime V prime. Okay, line segment SV is translated in the direction of GK. The measure of SS VV is the measure of GK. GK, capital GK. Heads in the way, Monty. Yep. The line segment S prime V prime is congruent and is parallel. Wow. Wow, wow. Okay. So now this idea of reflect, we want to reflect it. Okay. So we're reflecting PQ about JT. Okay. P prime Q prime is congruent to P, otherwise we would have failed, so true. The measure of PJ has to be the measure of JP. Has to be. QTTQ has to be. QQ is perpendicular, absolutely. Otherwise, it's not a reflection. Okay, to reflect means to stay perpendicular. Okay, so now we need to move this guy over here. The measure of SV is the same as SV. S prime M is equal to SM. V prime G to VG. GM is perpendicular to SS and VV, both. Otherwise, it's not a reflection. Okay, now we got to rotate. We got to spin it. Okay, so as we spin it, the key is where we rotate. Okay, and the reference point, the origin, or where the pin is, so that it spins around it. Okay, determine whether the statement is true or false. P prime Q prime has to be the same as PQ. Yes. The angle QWQ has to be the same, absolutely, otherwise it doesn't work. And it was rotated -60. -60. See, it went from here up, and counterclockwise is positive in math, so it was rotated -60 is false. Too bad they asked that. Okay, SV is rotated through a 75 degree, no, 75. See the 75 right there? That's the notation we're going to be stuck trying to learn, is notation. Okay, S prime V prime. S prime V prime is equal to the measure of SV. And the measure of the angle have to be equal to the +75, and they have to be both equal to VV, 75. Yep. Cool. Okay, so now perpendicular bisector. So if we draw a line perpendicular, boom, bisect, cut the angle in half. Okay, we have the perpendicular bisector theorem. Okay, decide whether each statement is true. RC, CB, true. PC to PR, no. RPC, BPC, yes, that's the whole idea of we cut it in half. If point F, use the diagram, F, where's F? If point F lies on PC, then FR FB. If G lies on PC, GB, GR. See what they're doing here is they're putting an imaginary point right here. Okay. Any distance from PC, my head's in the way. Any distance from PC, any point that lies on PC is the same distance from the points G and B. R and B. So any point here. Okay, replace P with any of those points. Okay, all right. So AC is congruent to CB. The distance from point P to A is the same as the distance from point P to B. The measure of ACQ has to be the same as BCQ. Oh, the measure, actual degrees. My bad. 90 degrees. Hey. Okay, so because we haven't been in class, that's a little harder to visualize, isn't it? All right. Let's see where that gets us to. Okay, so exploring rigid motion and dilation. That'll be next.